Welcome to week 10. Today, we're diving headfirst into the exciting world of automated machine learning or AutoML. Think of it as taking the manual, repetitive tasks of traditional ML and turbocharging them with automation. By the end of this session, you'll understand how tools like PyCaret, FLAML, and AutoKeras not only save time, but make machine learning accessible to everyone, beginners and experts alike. Let's automate your workflows and empower your creativity. This session is all about rolling up your sleeves and getting hands-on experience with AutoML tools. Expect a highly practical workshop combining live coding, small group challenges, and reflection points. Remember, AutoKeras performs best with GPU acceleration, so ensure you've set up your collab environment appropriately. Over the next 4 hours, we'll split our time between understanding concepts and diving face first into practical use cases. Stay engaged, curious, and ready to experiment. Here's a quick roadmap for today's session. Each part has been carefully designed to help you understand, explore, and apply AutoML tools effectively. By organizing our day into logical sections, starting with concepts and moving into tools and coding, you'll have a clear sense of progression as we move forward. In the first half, we'll start with the basics understanding AutoML. Have you ever wondered why machine learning feels like assembling IKEA furniture, tedious and full of decisions? AutoM is the Allen wrench that'll make your life easier. Then, we'll shift gears to tabular data where most practical problems happen. PyCaret will act like your cheat sheet for quick, no-fuss model building, while FAL focuses on speed and efficiency even on modest hardware. You get hands-on with both tools, so buckle up. In this part, we'll transition into the exciting domain of deep learning with AutoKeras. You'll witness how to simplify complex neural network design with just a few lines of code. After that, we'll introduce a fun, competitive model battle where you'll work in teams to apply what you've learned in real time. Make sure to bring your A game as we'll evaluate based on accuracy, speed, and explainability. Finally, we'll wrap up with reflections and key takeaways to solidify today's lessons. Let's keep the momentum going. Setting clear objectives is vital for effective learning. Today, we will focus on mastering AutoML concepts and tools. You'll gain both theoretical understanding and practical skills working across diverse datasets and tools. Whether you're completely new to AutoML or looking to deepen your expertise, this session will give you actionable insights to take your skills to the next level. Bloom's taxonomy provides a great framework for setting goals, and we'll use it to guide our learning journey today. You'll begin by learning and understanding key concepts like AutoML and NAS. As we progress, you'll get hands-on by solving applied problems with AutoML tools, moving on to higher order thinking like analyzing tool performance and evaluating their trade-offs. And to cap it off, you'll tap into your creativity by designing your experiments. Remember, the highest level of learning happens when you're able to combine knowledge with new ideas. Let's aim for that level today. Welcome to the core of today's session, AutoML. We're diving into what AutoML is and how it's transforming the landscape of machine learning. Think of AutoML as your co-pilot in the vast ML pipeline, helping with tasks like model selection, hyperparameter tuning, and evaluation. But in a fraction of the time it will take you to do them manually. It's not about replacing data scientists, but rather about amplifying their productivity and letting them focus on the bigger questions. By the end of this module, you'll have a solid grasp of what AutoML is and why it matters. When we say AutoML, think of it as creating a smart assistant for your machine learning projects. Instead of manually picking and testing models or playing trial and error with parameters, something that could take hours or even days, AutoL steps in to handle these repetitive technical tasks for you. It's like hiring a very disciplined intern who never gets tired. Let's get real for a second. Have you ever spent an entire weekend just tweaking hyperparameters like learning rate or number of trees in a random forest? Or tested dozens of algorithms without seeing major improvements in accuracy? It's frustrating and time consuming. Autumn turns this chaos into a structured, automated process. With tools like PyCaret or AutoKeras, even non-experts can produce results that rival those of seasoned data scientists, all while saving a ton of effort. Here's why AutoL is a game changer. It democratizes machine learning. No longer do you need years of study or access to specialized talent before building capable ML models. Imagine you're a marketing manager or a biology researcher. AutoM empowers you to explore predictions or automate repeated decisions without relying on a big team of data scientists. Plus, for professionals like you in the audience, it gives you superpowers, faster prototypes, scalable solutions, and the ability to focus on WHAT the results mean rather than HOW to get them. It's a workflow accelerator. This table shows how manual ML and AutoM differ at every key step. For manual workflows, you're spending a good chunk of time writing code for preprocessing, manually comparing several models, setting up parameter sweeps, then piecing all your results together. With AutoML, that work becomes automated and centralized. It's like comparing a hand cranked well to modern plumbing. Both deliver water, but one is clearly faster, easier, and scalable for the modern world. Take a moment to look at this condensed table. I want you to notice how AutoML steps in at the three costliest points in a traditional workflow. First, during data preparation, the automated pipeline now handles missing values, scaling, encoding, even basic feature engineering, all with a single line of code. Next, for model selection, intelligent search methods, think of FLAML's cost-aware hill climbing, can test dozens of algorithms in minutes, something that used to keep us busy for an entire afternoon. Finally, for hyperparameter tuning, techniques like Bayesian optimization or banded search replace the old grid search marathon and usually find better settings in a fraction of the time. The real superpower here is consistency. Once you define an AutoL pipeline, anyone on your team can rerun it and get nearly identical results without worrying about forgotten notebook cells or missing scripts. That is reproducibility made simple. Before we automate everything, let's be honest about where people still make a difference. A human in the loop approach shines when domain expertise adds real value. Imagine a radiologist adding custom features to medical images or a compliance officer in finance who needs a transparent model for regulation. On the other hand, fully automated pipelines are perfect for rapid prototyping, hackathons, or first pass solutions when speed is the top priority. In practice, most teams use a hybrid strategy. They let AutoML generate a strong baseline, then step in to refine, interpret, and govern the final model. So think of automation not as an all or nothing switch, but as a dial you set according to timeline, data complexity, and regulatory pressure. In this section, we'll introduce the three major tools we'll explore today: PyCaret for structured tabular data, FLAML when speed and resource efficiency are paramount, and AutoKeras for deep learning tasks like images or text. Think of these as tools in your ML toolkit, each designed with a specific strength. AutoML isn't just about saving time, it's about enabling you to focus on the creative, high-level aspects of machine learning, like designing experiments or interpreting results. Imagine having an assistant that handles the grunt work while you focus on the insights. Here's a high-level comparison of the three tools we'll explore today. PyCaret shines for structured, tabular data with its beginner-friendly, low-code approach. FLAML, created by Microsoft Research, is all about speed and efficiency, perfect for lighter hardware or rapid prototyping. AutoKeras taps into the realm of deep learning with neural architecture search NAEST, making it an exceptional choice for image or unstructured data tasks. Think of these as tools in a toolbox. Each is tailored for a specific purpose. PyCaret is your go-to tool when you need to work with structured data but don't want to spend hours writing boilerplate code. Imagine it as your Python ML Swiss Army knife. It preprocesses, trains, and visualizes in just minutes. For example, instead of deep diving into scikit-learn pipelines, you simply call a couple of commands like setup and compared models. The best part, it's fast, user-friendly, and great for experimenting or small-scale projects. FLAML's secret sauce is its efficiency. Think of it as the minimalist guru of AutoL. It strips away the unnecessary complexity to deliver fast and effective results. Want your ML model in under 60 seconds on a laptop? FLAML has your back. It's perfect for prototyping or when you're operating in a resource-constrained environment like running experiments on a shared system or cloud instance. It's all about doing more with less, and honestly, who doesn't want that? PyCaret is simplicity redefined. Imagine a tool that not only preprocesses data, but also compares models with just a single function. One standout feature is its interactivity. PyCaret's visualizations make it easy to see what your model is doing. Let's say you're curious about feature importance or performance metrics. You're just one click away. Plus, because it's built on scikit-learn, once you've identified your best model, you can easily customize or extend it further. It streamlines both experimentation and production. A true game changer for time-strapped practitioners. Florian is like the sprinter of AutoML tools. It shines when time and resources are limited. Imagine you're on a tight schedule or working on a laptop without fancy GPUs. FLAML gives you results without breaking a sweat. Its lightweight design doesn't mean it skimps on accuracy. It intelligently picks the best models and configurations in a fraction of the usual time. For this reason, Flail is perfect for those moments when you need fast insights but can't afford to wait for hours of training. We'll see how FLAL accomplishes this during the practical demo. Think of AutoKeras as the architect among Automan tools. Instead of you manually designing neural networks, AutoKeras uses NAS to draft and test multiple architectures until it finds the best one for your data. This is especially powerful for tasks like image classification or text processing that are traditionally tricky without deep expertise. A word of caution for optimal performance, you'll want access to a GPU. Deep learning on a CPU can feel like watching paint dry, so we'll make sure to enable GPUs when running AutoKeras. It's hands-free machine learning engineering at its finest. AutoKeras isn't just another tool, it's a paradigm shift for deep learning practitioners and newcomers alike. If you're working on complex tasks like classifying large image sets or analyzing text sentiment, AutoKeras does the heavy lifting. Think of it as hiring an expert consultant who tirelessly experiments with architectures behind the scenes. The GPU scalability is the cherry on top, so don't forget to enable hardware acceleration before diving in. This makes it accessible even if you're not an expert in TensorFlow or Keras. Now let's shift gears and focus on PyCaret, your go-to tool for automating machine learning on tabular datasets. Think Excel sheets but powered with AI. PyCaret is all about simplicity. In just a few lines of code, it takes care of preprocessing, model selection, and even tuning. This hands-on section will showcase how PyCaret not only saves you time, but also makes machine learning accessible, even if you're just starting. We'll dive right into a live demo with a real world dataset, so get ready to see PyCaret in action. PyCaret is like a Swiss Army knife for tabular data. It's beginner-friendly yet powerful enough for professionals who want rapid prototyping. Instead of worrying about the nitty-gritty, it takes care of tasks like normalization, encoding, and even model comparison. Here's the kicker: with just a few lines of code, you're running comparisons that normally take hours. Whether you're a student or a seasoned analyst, PyCaret drastically lowers the barrier to entry. Think of these steps as a conveyor belt for machine learning magic. First, PyCaret prepares your data. No manual cleaning or transforming needed. Next, it conducts a model bake-off to identify the best performer. Finally, it offers you the chance to improve results at the granular level or export the model for your real-world use case. These three steps give you both speed and quality, cutting time and frustration in half. Here's where the magic starts. This sample code sets up the Titanic dataset for classification. Will a passenger survive or not? PyCaret takes care of messy data details like missing values, one hot encoding, and scaling, all with one command: setup. The session ID ensures reproducibility for consistent results. Even if you're handling much larger datasets, this approach holds and saves immense time. In just two lines of code, you can compare models and visualize performance. Compare models, trains multiple algorithms, ranks them based on performance metrics, and returns the top model. You can even use plot a model to instantly create insightful visualizations. Here, a confusion matrix for classification tasks. This automation helps you make data-driven choices without manually configuring or testing multiple models. It's efficient, intuitive, and perfect for both new and experienced developers. One of PyCaret's major strengths is its ability to provide comprehensive insights into the models it generates right out of the box. For example, when you use compare models, you'll get a pre-sorted list of algorithms ranked by their performance. On top of that, PyCaret makes it easy to visualize key details, like a confusion matrix to see where your model performs well or struggles, and feature importance plots to understand which variables drive predictions most. Best of all, it even interprets what's under the hood, so you're equipped not just with results, but the why behind them. This makes PyCaret an excellent tool for efficiently moving through model exploration and analysis. Now let's zoom in on a tool designed for speed: FLAML. This chapter explores how FAML can help you achieve competitive results even in resource-constrained environments. We're talking about quick experimentation without sacrificing accuracy. Its use of advanced optimization algorithms and focus on simplicity makes it ideal for projects where time and computational power are limited. Freon stands out because it allows you to optimize for speed without compromising much on model performance. If you've ever been frustrated with long training times or extensive preprocessing, FLAML is here to remove those headaches. You can dive straight in, raw data, minimal setup, and voila, it's particularly great for students or researchers working on machines with limited computational power. Imagine being able to run experiments quickly on your laptop without needing access to a high-performance GPU cluster. That's the kind of efficiency it delivers. Let's delve into what makes FLML tick. Instead of blindly searching every possible parameter like traditional model tuning processes, Fourier employs cutting-edge optimization techniques. This is particularly handy when you set a time budget. Say, find me the best model in just 1 minute. It'll evaluate multiple algorithms and configurations under those constraints. Plus, Farrell doesn't limit itself to one type of task. Whether it's regression, classification, or ranking, you name it. It simplifies the process while keeping results competitive. It's like having a fast, efficient assistant running the show for you. This is how you can use FLAML for a quick regression problem. Notice how minimalist the code is. FLAML handles everything under the hood, from preprocessing to selecting the best model and configuration within the specific time budget. You could use this approach for predicting housing prices, stock values, or any numerical problem you're working on. Also, you can access the best model configuration and gain actionable insights into what FLML has picked for your data. The beauty of FLAM lies in how it balances speed and accuracy. It's not trying to find the absolute best model ever, it's looking for the best it can achieve within a limited window of time. This makes it ideal for situations where you're experimenting or on the go, like when running tests on a laptop. In practice, it's a game changer for resource or time-limited scenarios. Let me explain why FLML is such a great asset, especially for your day-to-day projects. Imagine you're working on a tight deadline and can't afford hours of grid search across multiple models. Or maybe you don't have access to a high-performance GPU, just your trusty laptop. FLAML shines in these scenarios by being super efficient, lightweight, and requiring little manual involvement. Its simplicity is its power, making it a favorite for practical real-world ML tasks. The standout features of FLAML make it more than just an AutoML tool, they make it indispensable. You might wonder how does it differ from tools like PyCaret? While PyCaret focuses more on user-friendly end-to-end workflows, FLAM keeps things extremely lightweight, stripping complexity down to its essentials. It's perfect when you want results fast without sweating the tiny details. Essentially, Flail is the minimalist's dream. Powerful yet simple. ForML shines when timelines are tight or computational resources are constrained. Imagine you're working on a tight deadline to deliver initial predictions or you have access to only a standard laptop. That's where FRAML steps in. It optimizes not just for accuracy but also for practicality, quickly building models without the usual trial and error overhead. It's perfect for tasks like predicting house prices or identifying key customer segments without burning out your hardware or your patience. Let's walk through this example. In just 60 seconds, Faleo will automatically select and train the best regression model for predicting house prices. The auto object is like your assistant. It searches through possible models and configurations for you. Then you can access the best estimator to see which model it decided on and review the performance metrics. This simplicity is part of why FOL stands out. It saves both time and compute, making it an incredibly efficient tool for day-to-day machine learning tasks. This code is straightforward but powerful. First, we initialize the auto object, which prepares FLAML to start searching for the best model. The fit method does all the work: data preprocessing, model selection, hyperparameter tuning, and evaluation. Notice the time.budget 60. This is where the magic happens. Even with such a tight time constraint, FLAML delivers a trained model with solid performance, making it a great choice for quick turnarounds or when experimenting with small datasets. Once FLAL gives you the results, what do you look for? First, the best estimator tells you which algorithm performed the best. In our case, it might be something like random forest regressor or LightGBM. Second, check the metrics it outputs, such as RMSE for regression tasks, to see how well the model performed. Lastly, don't forget to try out predictions with real data or integrate these results into a larger workflow. FLAM isn't just for beginners, it's also perfect for prototyping or augmenting existing machine learning pipelines with efficient experimentation. Welcome to this chapter on AutoKeras. We'll explore how deep learning can be made significantly easier using AutoKeras and neural architecture search. Think of this as allowing a tool to decide how to construct the perfect neural network for your problem, letting you focus on results rather than the technical nitty-gritty of architecture design. By the end, you'll see how AutoKeras can dramatically simplify image data experiments, especially when utilizing GPUs for training efficiency. Now, before diving into AutoKeras, let's talk hardware. Neural architecture search, and as involves testing many possible model architectures to determine the best one. It's essentially trial and error on steroids. Training on a CPU will work, but it'll feel like walking a marathon when you could be driving a race car. GPUs are built for this kind of parallel processing, shaving hours off of training time. If you're using Google Colab, switch to GPU under runtime. Trust me, future, you will thank you. Imagine trying to bake a cake without knowing the recipe. You might experiment with different ratios of flour, sugar, and eggs until you finally get it right. Neural architecture search. NAS does something similar for neural networks. It intelligently experiments with various architectures to find the best recipe for your dataset. For example, it decides how many layers, what activation functions to use, and how the layers should interact. This automation is especially game-changing for non-experts as it removes one of the most challenging parts of deep learning. So, why should you consider AutoKeras over traditional deep learning frameworks? In a nutshell, it's like having a GPS for navigating deep learning. Instead of manually building and tuning architectures, AutoKeras takes on the heavy lifting, helping non-experts achieve results comparable to those of experienced practitioners. It's especially effective for tasks like image classification, where figuring out the right architecture could take weeks. Think of it as your co-pilot. You set the destination serial dataset, and AutoKeras plus the fastest, most effective route to success. Alright everyone, let me walk you through this code. We're using the famous CIFAR 10 dataset, 10 small object classes that are a rite of passage for any computer vision project. I import AutoKeras, load the data, and then create an image classifier. The key setting is max trials equals 5, which simply means AutoKeras try up to 5 different neural network blueprints and keep the best one. After that, I call fit for 15 epochs. While it's running, watch the log in your notebook. You'll see AutoKeras experimenting with different architectures and stopping early when it finds something promising. When the training finishes, we evaluate on the test, split, and print the accuracy. Notice how little work that took. No manual model design, no handwritten training loop, yet we'll still get a respectable score. Let me unpack the most important arguments you just saw. Max Strauss controls how wide the search is. If you're just exploring, a small number like 5 keeps things quick, but if you have time and GPU budget, you can turn it up for a deeper search. Override equals true tells AutoKeras to forget any previous runs, handy when you're tweaking experiments and want a clean slate. Epochs is the number of training passes for each candidate network. More epochs give better convergence, but obviously cost more time. Finally, the evaluate function returns loss and accuracy on unseen data, giving you an honest report card. Think of these settings as the dials you turn to balance speed against performance. What makes AutoKeras special is the way it hides the messy parts of deep learning. Behind the scenes, it is running neural architecture search, the same family of techniques Google used to invent EfficientNet. It handles the boring chores too, like resizing images, normalizing pixel values, even splitting your data into train and validation sets. In practical tests, I can hit 80+% accuracy on CIFR, 10 in under 10 minutes on a free Colab GPU. That's why I call AutoKeras my one line research team. It gives beginners a fighting chance and lets experts prototype ideas at warp speed. Quick sanity check before we dive deeper. Make sure your runtime actually has a GPU. In Colab, open the runtime menu, choose change runtime type, and pick GPU. Then run TensorFlow's list physical devices call, and you should see at least one CUDA device. On CFAR 10, the difference is night and day. A full search that takes 2 hours on CPU usually wraps up in 6 or 7 minutes on GPU. If you're on a paid cloud, remember that more trials and longer epochs will rack up costs, so start small, profile the time, and scale up once you know the value. So why is AutoKeras my default choice for image projects? Because it removes guesswork from architecture design. Instead of debating whether you need 3 convolution blocks or 5, you let the search algorithm figure it out. That freedom is priceless when you're working with unstructured data like photos or medical scans where feature extraction is not obvious. AutoKeras also exports a standard Keras model, so deployment to TensorFlow serving or conversion to TensorFlow Lite is painless. In other words, fast experimentation upfront and straightforward production workflow at the end. Now it's time to put your knowledge into practice with a friendly competition. In this activity, you apply everything we've learned about AutoML. Gather your team, pick a dataset that excites you, and see how well you can utilize PyCaret, FLAML, or AutoKeras to create the best performing model. The goal is not only accuracy, but also speed and explainability. Let's see who can balance these factors best. The instructions here are crafted to ensure you enjoy the experience while also digging deep into the strengths of the AutoL tools. Encourage your team to discuss which dataset they want to tackle. It could be a challenging structured dataset or something creative like analyzing memes for popularity. This activity isn't just about winning. It's about learning how to critically evaluate results across multiple dimensions. Involve everyone in your team and remember to share the workload. We're using 3 key metrics to keep things fair and comprehensive. Accuracy is critical, of course, because a model needs to make good predictions. But speed also matters. You might have the best predictions in the world, but if it took hours to train, it isn't practical for many real-world applications. Lastly, explainability ensures you understand why the model works. Bonus tip: tools like PyCaret have built in explainability visualizations. Make sure to leverage those. For the bonus challenge, you have a chance to dig deeper and contrast human expertise with the convenience of automation. This will help you understand where manual tuning excels and where AutoL shines. Don't just try to beat AutoML. Carefully evaluate how much effort it took to get better results, if at all. Try to highlight the time trade-off or specific cases where your domain knowledge added value. This will make your results even more insightful. This table outlines the three main metrics we'll use to judge your models. Accuracy measures prediction reliability. It's the first thing that will tell us how well the model works. Speed matters because faster models are essential for environments where time or resources are constrained, which is a real-world consideration in many projects. Finally, explainability is about clarity. It's not enough for a model to deliver numbers if end users or stakeholders can't understand the why behind the predictions. Each metric on this list serves a unique purpose. For accuracy, think of a weather forecast you trusted when it consistently gets predictions right. Speed is like driving on the highway. It's not just about reaching the destination, but also how quickly you get there. Explainability is critical, especially in fields like healthcare or finance. Imagine trying to convince a doctor or banker that your black box algorithm works without being able to explain it. They'll be skeptical, right? You want to understand the why yourself and be able to showcase it to others. Think of accuracy as the cornerstone of any machine learning model. After all, what's the use of a blazingly fast model if it can't predict correctly? However, high accuracy isn't always the full story. For instance, in the Titanic survival example, a false negative predicting someone didn't survive when they actually did can be much more damaging depending on what you're modeling. Frame accuracy within the problem context. It's about both precision and purpose. High percentage doesn't always mean high utility. Speed can make or break your workflow. Think about practical scenarios. Your time boxed in a Kaggle competition or have limited GPU compute credits. In these cases, speed allows quick model iterations, giving you flexibility to try more things in less time. For FML, it's like having a fast, no, frills race car. Not flashy, but perfect for structured tabular tasks on limited budgets. Explainability is a crucial aspect of machine learning, especially in sensitive areas like healthcare and finance, where lives or finances may be affected by model decisions. Think of SAP as a translator. It tells us in plain terms which factors influenced the outcome the most. For instance, if your model's predicting loan approvals, SAP can show whether income, credit history, or education level played the biggest role. This level of detail doesn't just foster trust, but can also help fine-tune models for fairness or adapt them for specific requirements. Remember, a model's power comes not just from its strength in prediction, but from how well we understand and apply its insights. This challenge is like a battle royale for machine learning methods. You pit the lightning-fast, automated approach against the precise, hands-on manual tuning. Manual tuning gives you control over hyperparameters, like picking the perfect recipe for cookies. Finer control means potentially better results. On the other hand, AutoML takes the guesswork out, like an automatic cookie factory that adjusts flavors on the fly, but which makes the tastiest batch in the shortest time. Be honest in comparing both. You'll get insights not just into the models, but also into your own workflow preferences. In this part, we manually tune a random forest model using grid search CV. Our goal is to predict survival on the Titanic dataset based on features like class, gender, age, fare, and port of embarkation. First, we preprocess the data by encoding categorical variables and splitting it into training and test sets. Then we define a parameter grid, which includes different values for the number of trees and the maximum depth of the trees. Grid Search CV goes through all combinations and picks the best one using cross-validation. This process is like experimenting with different temperatures and baking times to get the perfect cookie. Our best model used 50 trees and a max depth of 10 with a test accuracy of about 75.5%. While this approach gives us hands-on control and teaches us how models behave, it also takes time and requires manual effort. Keep that trade-off in mind as we compare it to AutoML on the next slide. Now, let's look at the AutoML approach using PyCaret. Here, instead of manually coding and testing different models, we use a simple setup function that handles preprocessing and modeling for us. Then, with just one line using compare models, PyCaret automatically tests a wide range of classifiers and picks the best one. In our case, the gradient boosting classifier performed the best with a test accuracy of 78.3%, which is slightly better than our manually tuned random forest. This is the strength of AutoML: fast, efficient, and beginner-friendly. But remember, AutoML tools are only as good as your understanding of the data and the context. As you reflect, ask yourself which method was easier to implement, which was faster, and which taught you more about model behavior. Manual tuning deepens understanding. AutoML speeds up experimentation. Mastering both approaches will make you a more flexible and effective machine learning practitioner. This is an opportunity to critically evaluate your workflow. Start by asking yourself, was AutoML's speed worth the potential trade-off in transparency? Or did manual tuning's flexibility provide a noticeable edge? Reflect deeply on what worked and what didn't. Did you find a creative solution to overcome data issues or optimize a model faster? Share these learnings in team discussions. They'll not only solidify your knowledge, but contribute to everyone's understanding. After all, machine learning is by nature iterative. The best models and workflows emerge after honest review and continuous refinement. This chapter dives into the benefits and limitations of AutoML. While AutoML seems like the magic bullet, every tool has its trade-offs. We'll explore when and why to use AutoML and when a manual, hands-on approach might work better. I'll also provide real-world insights to help you decide the best approach for your projects. Autom is often marketed as drag and drop machine learning, but it's more than that. The biggest benefit? Time. Instead of spending hours or even days tuning hyperparameters manually, Autom can deliver functional models in minutes. Plus, it democratizes ML. Imagine being a complete beginner and still building a competitive model using PyCaret or FLAML. And for professionals, it's a huge productivity boost, allowing data scientists to focus on strategy and model interpretation rather than repetitive technical details. While AutoML is powerful, it's not a silver bullet. Let me give you an example. Imagine you're working on a rare disease dataset. AutoML might struggle picking the right architecture unless it's been finely tuned for highly imbalanced data. Another issue: debugging. If the AutoML process doesn't converge or makes odd decisions, it becomes a black box. It worked or it didn't, but you might not know why. And remember, AutoML still requires significant resources, particularly for deep learning tasks using tools like AutoKeras. So, treating AutoML as a productivity powerhouse rather than an all-knowing oracle is key. So when does AutoML truly excel? Think startup environments, small datasets, tight deadlines, and limited GPU power. AutoL thrives here by quickly giving you an actionable model. It's also great for brainstorming sessions. Imagine needing to test several ideas without spending weeks on preprocessing or coding custom pipelines. And for less experienced teams, it flattens the learning curve and lets them produce results they can immediately use in decision-making processes. It's a tool you'd reach for to get things started or when the goal is to iterate fast, not necessarily when you need granular control over every detail. All right? It's time to pause and reflect critically. These questions are designed to challenge your understanding of AutoML. Start by asking yourself, what are AutoML's blind spots or limitations? For example, while AutoML often does exhaustive searches, sometimes the best found model might not generalize as well due to overfitting, limited hyperparameter options, or even noise in the data. Now, think about preprocessing. Can you come up with a scenario where domain expertise, like engineering a specific feature, could completely alter your results? This is where humans still have an edge. Finally, for debugging an auto pipeline, consider issues like bad training data, incorrect configurations, or performance bottlenecks. Remember, AutoM is powerful, but knowing its limits is what will make you a true ML expert. Let's wrap up everything we've learned so far. Remember, AutoM is not here to replace you, it's here to assist and amplify your skills. Whether it's PyCaret or AutoKeras, you now have the tools to automate tedious workflows and focus your energy on what matters, building impactful solutions. And keep in mind, the more you explore what can and cannot be automated, the more value you'll bring as a machine learning practitioner. Take a moment to absorb what you've accomplished today. AutoL has simplified complex workflows, but it's equally important to know when to step in and take control manually. This is your main takeaway. Automation makes you faster, but your human judgment is irreplaceable. Remember the key points about each tool. PyCaret for structured datasets, FLAML for quick experiments, and AutoKeras for tackling deep learning problems. Now, you're equipped to evaluate the strengths of these tools and even combine them with your expertise for superior results. Time to get creative. Think of this challenge as your chance to apply what we have learned on something you care about. For example, if you're into music, use a dataset of your listening history from Spotify. See if you can predict your mood based on song preferences. Or for those of you who love visual data, try using AutoKeras for image classification tasks like sorting your photo gallery. Post your project findings on the class forum. We'll celebrate the most creative and executed entries next week. Remember, the goal isn't just accuracy, creativity and insights matter too. These projects are designed to blend fun and learning. For the Spotify mood analysis, download your streaming history, feed it into PyCaret, and see if the algorithm can predict your mood for given songs. For the photo gallery classification, AutoKeras simplifies creating a high-performing image classifier. Think about categorizing photos efficiently, and for those who love competition, compete by benchmarking PyCaret and FLAML. Test performance across metrics like accuracy and speed, and share visual examples. Let creativity drive your learning. Let's reflect on what we've achieved. Automate tools like PyCaret, FLAML, and AutoKeras helped us reduce hours of manual work while exploring full pipelines for tabular datasets and images. Yet, automation isn't a substitute for understanding, it's a partner. Just like a co-pilot ensures smooth flying but relies on you to navigate storms, AutoML frees your time to think critically and design impactful applications. Remember, automating the process is a starting point, but interpreting outcomes is where you shine. That brings week 10 to a close. First, double check your GPU settings. It will save you hours. Take a quick stretch so you come back with a clear head. And remember to fix the imbalance flag in PyCaret will bail you out if the encoder trips over rare categories. For next time, I'd love to see what you've built. Each team will have a few minutes to show off results, answer questions, and collect quick feedback. Use that input to refine your final presentation. Thank you for the energy and curiosity today. Keep experimenting and have a fantastic week.